पीपीटी शेयर रखें क्या? अच्छा मोनिश,
यस मैम।
जब तुम्हारी बारी आएगी तो क्या मैं अनशेयर करूंगी स्क्रीन, तुम शेयर करोगे अपनी तरफ से?
हाँ।
ठीक है। हाँ, नहीं बंद कर देना, जब होगा तो बंद कर देना, अभी बंद कर दो। हाँ, नहीं ठीक है, पंखा ठीक है। नहीं बंद बंद रहने दो। आप बाहर कुछ आवाज होगी तो आवाज आएगी ना फिर। चलो। Hello, good afternoon, everyone. Namaste, everyone. Uh, Welcome you all to the today's webinar on simplifying additive manufacturing processes using AM Pravah. My colleague Mohnish Soral and I, Dr. Rimchim Gupta, welcome you all on behalf of Paanduv applications to this webinar. This is the part 2 of AM Pravah webinar series. Uh, we are sitting comfortably in our office at Bareilly, which is located in India. It was raining heavily outside a while ago, and now the temperature is around 28 degrees Celsius. And if you cannot locate us through your visual map, we are located near the foothills of Himalayas, which is also near to the Nepal border. So let's begin with today's webinar. And through this webinar, we aim to understand how AM Pravah can simplify the complex AM processes by streamlining and by optimizing the overall additive manufacturing process for real-time industry scenarios. By the end of the webinar, our listeners will be able to understand and they will be clear on how AM Pravah can help industry to reduce the production time as well as the cost associated with additive manufacturing experimentations and overall process. Before proceeding further, I want to give you a disclaimer that all the animations and all the simulation images or animations are generated using AM Pravah in this session. So let's have a quick recap on the AM Prabha webinar series part 1, which was delivered by my colleagues Prithvi Uttarwar and Manya Gupta. Through this webinar, we aimed to highlight on the recent advances and recent developments that we have made in additive manufacturing software AM Prabha to make it more accurate, faster, and more user friendly. I have also compiled a presentation that will spark your interest for the today's session. Let's just have a quick glimpse of the previous webinar. So in today's webinar, we are focusing on two processes. The first one being the LPBF or laser powder bed fusion, in which there is a layer by layer spreading of powder. And when the laser is subjected onto the powder, the multiple physics phenomena occur, such as melting, vaporization, solidification. And this is an intrinsic physics that we are trying to capture using AM Prabha. And the second process that we are going to capture in today's session is W-LAM, which is also called the wire-based laser additive manufacturing, or in general terminologies, it is also called wire DED, direct energy deposition. So when we talk about metal additive manufacturing, there are multiple industries in which metal additive manufacturing is being used, but aerospace and defense industry and medical and healthcare are coming at the forefront. They have been started using 3D printing in real-time applications. One such example is the 3D printing of liquid rocket engine by ISRO, and which is done by LPBF. Through this process, they were able to reduce the material usage by 565 kgs to 13.7 kg of metal powder, and this could cut down the production time by 60%. Now, if I want to fit AM Pravah in this scenario, we aim to reduce the production time further and reduce the overall cost associated with these experimentations even further and associated with the resources as well. So Apart from this, if I talk about the medical and healthcare scenario, there are certain implants such as brain implants, facial implants, knee implants, or rib cage, etc. The customization is very important in those industry, along with the alloy development. So again, AM Pravah can be a savior here as well, because through AM Pravah you can understand whether the material or whether the alloy is printable or not. So the printability can be gauged by using AM Pravah. Now let's go back in time a little bit, and let's go to 2021 when we started developing AM Prabha. We started with three-phase multi-phase system, and we used constant surface tension uh, analogy there, and we developed a flat and very simple GUI for our users, and we are thankful to our people who trusted us with this version. And then we proceeded further for 2022, where we enhanced the solver, or the development was done on the temperature dependent surface tension addition in the solver. We also concentrated highly on validation and verifications of our results, and we created a manual related to that. In 2023, we transformed from three-phase multi-phase system to four-phase multi-phase system. And in the commercial space, this was the first time when somebody used four-phase multi-phase system. We also incorporated the effect of Fresnel coefficient, which takes the optical properties of the powder into account. We also developed a dark themed graphical user interface, which was very easy for user to use. Now we are in 2024, and we are going to soon launch our EM Prabha version 1.9 or version 1.2, where we are going to incorporate LPBF, which is laser powder bed fusion, with wire lamp. And again, we have incorporated four-phase multi-phase system, but the new things here are addition of non-spherical particle spreading, laser beam shaping, temperature-dependent surface tension, as well as thermophysical properties of alloy, the user-friendly graphical user interface, and we have equipped the software with advanced techniques for reducing the computational time, and this is also equipped with smart parallelization. Now, let's connect the dots for today's session. We will start with knowing some of the physics about the process, and then we will understand, and I will elaborate the LPBF case study in more detail. Then my colleague will take over, and he will demonstrate and elaborate on the case study related to wire LAM, and then we will summarize and conclude the webinar by giving you some updates and some recent events that happened for today's in the recent time. So let's just summarize what are the current and upcoming capabilities of AM Prabha. We are doing spherical and non-spherical powder distribution. We are taking all the optical properties into account. Multiple reflections is one of the key parameter to understand the keyhole defect, and that we are capturing in good detail. We are having the four phase multi phase system into account, and laser beam shaping is included already. We can also improve the accuracy by taking the temperature dependent thermophysical properties of alloy. We are taking into account all the Marangoni convection effects, recoil pressure, because four phase are included, that means vapor is already included, hence the real time effect of recoil pressure is also included. Since we are also having the module of microstructure analysis, which gives you Euler angles, polar plots, and misorientation angles as the result, and through which you can get the 2D and 3D complete data of microstructure with the mean grain size analysis as well. And finally, last but not the least, we also have the deep learning module, because people who are generating a lot of data, who do not know how to deal with this data, we can help you with that, and our deep learning module can help you with that. Now let's just scratch the surface a little bit and know more about the melt pool. There are We can categorize the melt pools in three categories. The first one starting from conduction mode, transition mode, and the keyhole mode. Conduction mode being when the aspect ratio of the melt pool is around 1, and when it starts getting greater than 1, it goes to the transition mode, and thereafter it goes to the keyhole and porosity mode. So now when we have the conduction mode in place, that means the laser power is not enough, but it is enough to create the recirculations in the melt pool. The whole melt pool dynamics happen because of the surface tension effect, because of the higher temperature. The locations where the temperature is higher, the surface tension will be low, but the locations at the edges where the temperature is lower, surface tension will be high. So the liquid always try to move from lower surface tension areas to higher tension areas. And in this context, the forefront of the laser beam is always forms a clockwise vortex, whereas the part which is behind the laser always forms the anti-clockwise vortex, and which can be seen from this particular image at the bottom. Now when the laser energy increases, it creates a depression, or it creates the deeper penetration in the melt pool, and which starts the inclusion of vapor in the melt pool, which also increases the porosity in the part, which is not a very likely phenomena for the experimentalists. We want to eliminate this process, but in this case the melt pools are quite wider, and we can separate, or we can compartmentalize the overall melt pool in three parts. The first one is tail, which is the back of the melt pool. The second part is body, which is the middle of the melt pool. And the first part is the head, which is the forefront of the melt pool. And you can see, because of the length of the melt pool and complete temperature gradient, the flow always wants to go to the backside, but due to the longer path length, the flow deviates a little bit, and that's what you can see from this particular animation, this particular image. So the overall melt pool dynamics is the complex interplay of five forces. The first one being the Marangoni convection, recoil pressure, buoyancy effect, gravity, and the viscous forces. Now, when the melt pool moves from conduction mode to the transition or to the keyhole mode, there is a dominance of different forces that we can see. When we go to the keyhole mode, the recoil pressure starts dominating, which tries to keep the melt pool open, but at the same time Marangoni convection tries to minimize this effect, and it tries to close the keyhole formation. But because the recoil pressure dominates, there can be some inclusion of vapor into the melt pool, which gives rise to the porosity in the part. Now let's understand and let's know why we are emphasizing a lot on four-phase multi-phase system and what are the distinguishing features of AM Pravah. The first one, I would again highlight the four-phase multi-phase system, which brings us closer to the accurate results. When we try to minimize the assumptions, we are automatically moving closer to the actual results. The second thing is that it is a comprehensive solution, and in future we want to make it a one stop solution for all the AM processes to model. So far we have included macro scale module, which gives you a complete detail of melt pool dynamics and defect mitigation and the defect formation. And we have also included the microstructure analysis, and the third module is deep learning module, and we are working rigorously to make all the modules even more robust, and we are doing that non-stop. The third part is scalability. The software can be used for multiple processors without an additional cost. And the fourth point is the user specific graphical user interface. That means the we have made the software not only for the people who are well versed with computational modeling. The software can be used from students to material scientists to metallurgists to experimentalists and to the people who are proficient in computational modeling. So it completes the arc of the users that want to use am additive manufacturing processes. Now again, highlighting more onto why four phase system is important, because when when the temperature reaches to the vaporization temperature, the vapors starts forming, and it exerts a inward force onto the uh, onto the uh, onto the vaporized surface, which is perpendicular to the vaporized surface, and the temperature and the velocities can be much higher in those regions. The velocities can go from hundreds to 1,000 meter per second, and there is a friction between the liquid and gas interface, which is imposed in those scenarios. And if you use some empirical correlation, this can not mimic the exact processing or exact physics of the process. Hence, phase as it is important to include. And in am Pravah, we are trying to capture all the four phases, and these are simultaneously tracked at each time. Giving you a little bit brief about the keyhole formation. As I indicated earlier, there are two forces which are responsible. The first force is recoil pressure, and the second force is capillary forces or the Marangoni convection. The recoil force or recoil pressure tries to open the keyhole, whereas the Marangoni convection tries to close the keyhole. But because recoil pressure dominates in all times when the vapor plume is ejecting, there is a possibility that vapor may trap inside the system, and it can give rise to the keyhole porosity. Now we are at the intersection of laser powder bed fusion as well as wire based laser additive manufacturing, and we are modeling both of the processes. Now let's jump directly to the case study for LPBF. We have modeled here for 5-layer 2-track LPBF system, which is a cantilever kind of a structure, which is quite difficult to print in additive manufacturing. So the aim of the study is to understand how to deduce and get important parameters that industry requires. So this is the scan pattern that is also generated using AM Pravah. We have provided a tab in graphical user interface to visualize the scan pattern, and through which you can visualize the scan pattern in this format. Some scan pattern related details such as hatch distance, hatch offset, hatch delay time, which is very important. Just notice zero point 0.6 millisecond, because in the after some slides I will change this delay time and show you the results for this particular study. The material here is Ti64. The laser power is around 266 watts. The scan speed is 1 meter per second. Layer height is 60 micrometer, and the preheating is 323 Kelvin. One interesting aspect of AM Pravah is also adjustment of the accuracy. Once you adjust accuracy from 10% to 100%, your mesh size changes in this fashion. And this change is non-linear. Therefore, the accuracy will improve significantly when you go from 20% to, let's say, 60% or 70%, because the mesh size is completely changing. Hence, when you require uh, for your model to take less time for the process, you can adjust your accuracy accordingly. This is a flexibility that we have provided to the user. Now, the first part of the LPBF modeling is spreading of the powder. So already you can see from the animation, 4 layers are already printed. And one important thing to focus here, that AM Pravah takes the correct topology of the previous layer into account before spreading the next layer. These Layer spreading is not independent, these are all coupled. That means any discrepancy in the fourth layer spreading will change the spreading of the fifth layer. So these are all coupled in itself. Next is the melt pool dynamics for 5 layer 2 track system. And you can see the temperature evolution here for the melt pool, which goes from 1000 to 6400, which is 6000. And there are very small regions where the temperature is reaching that high, but the average temperature always remains around 4000 to 500 5000. So we have taken out the melt pool dimensions, width and depth. We have cut slices in 2D, in X direction, Y direction, and we understood the system very well. And the width of the AM Pravah simulation came out to be 107 plus minus 8, and the depth is coming out to be 72 plus minus 8 micrometer, whereas the literature suggests that these values can be in the range of 122 plus minus 13 and 80 plus minus 10, which gives us the error percentage of below 15% in all the cases. We have also compared these results with the experimental values, which is in quite good agreement with that. These are some of the literature that I have listed. But now let's understand and let's see how visually these scans look like. At each layer, we can see there is a correct Marangoni convection is taken into place, because wherever there is a deeper penetration, the surrounding liquid is moving in upward direction, and that indicates that the fluid is moving in right direction. In AM Prava, we have also given the opportunity for the user to take out only the build part or the solidified part, and thus by getting this build part they can further analyze it to get the specific localized density, specific localized temperature, and complete history of different parameters. So if we closely analyze this build part, there are different regions where we can see the lack of fusion between the hedges and lack of fusion between the layers. This itself indicates that the hedge spacing is not enough to merge the two melt pools together, and which will give you the porosity defects further, lack of fusion defects further. We also saw the pore formation in some of the parts, and one part we have highlighted here. This may be because there was already a void because of the particle distribution, and when the laser hit these particles or melted these particles, this pore shifted little bit in the left. So this may also give rise to the porosity defect. We also observed at some of the places that there is a deeper penetration of the laser in some parts, which can lead to the transition mode uh, of uh, melt pool dynamics. Now, as I indicated earlier, that the hedge spacing is not enough, but still the hedge delay time is varied in all the simulations. That means we have taken now 0.6 millisecond as the hedge delay time, and corresponding to that we can also have an estimate of the average build temperature in across the region. And once we have this temperature data, we can further analyze it to get the cooling rates, and we can see that the cooling rates are in the range of 2 into 10 raised to power 6 Kelvin per second. Now in this animation we have changed the hash delay time. We have kept all the parameters exactly the same. Only change in this simulation is changing the delay time to 0.35 millisecond from zero point 0.6 millisecond. And let's see how this changes our system. Now we have plotted the cooling rates for that system where we have kept the H delay time 0.35 millisecond, and the second one where we have kept the H delay time 0.6 millisecond. And we found some difference in magnitude of the cooling rate, which comes to be around 3 into 10 raised to power 6 from 2 into 10 raised to power 6. And also the peak temperature for each build also increased when the hash delay time is 0.35. That means it is experiencing a lot of heat heat cycles when the laser is moving from one direction to the another, and the further movement of laser is affecting the previous layers. To analyze it further, what we had done is we have built a thin walled structure of 10 layers of Ti 64 using AM Pravah, and we analyzed we had left a probe somewhere here and we analyzed the temperature distribution. We saw that up to third layer, the temperature of the third layer is affecting the temperature of the first layer, but after that, when the laser hits the fourth layer, there is no effect on the first layer for that. That means after the three layers the temperature is getting steady. That means those are the results that we can rely on. Therefore, we left these three layers and we took the porosity in the upward direction. We cut a cube in all the directions and we analyzed the porosity and the density in those regions. And the density, average density, comes out to be 4392.17, whereas the bulk density is 4420, which gives us the porosity of 0.63%, whereas the experimental porosity comes to be around 0.5%. Similarly, we also analyzed the surface roughness around this region, the extended parts or the discrepancies around the edges we took into account, and we finally came up to a number of surface roughness around 32 micrometer, and the experimental values for these things can be from 10 to 50 micrometer in range. This is not the exact visual validation from the experimental data, but we have taken this image from the literature. This is just to show you that if we cut a cross section for a thin walled structure, it can look something like this. There can be some lack of fusion defects. There can be the powder spreading in this manner, which quite resembles with the images that we are getting. And there are problems at the edges at the because that can give rise to the surface roughness, and there are problems inside the part which can give rise to the lack of fusion defects. We also further analyzed the microstructure analysis, and this is the one for 5-layer 2-track multi-phase system. We had cut the part in such a manner that you will be able to visualize all the 4 5 layers. Now, once we get this 3D data, we can further analyze it to get the polar plots and the slices or 2D data in different direction and different planes. And this whole data is provided to you by AM Pravah only. These polar plots will indicate that at this particular plane, in which direction my grains are oriented. And there are some numbers which will give you the size range of the grains in that particular direction. We can also further analyze the grain size distribution for this particular system, and here we have got the grain size of around 9.96 micron when we use Hall patch equation, which is analytically proven formulation for getting the yield stresses, hardness, fatigue, etc. When we put this number into this uh, formulation for Ti 64, we get the value of 986.99 megapascal micrometer to the power minus half, whereas we have we have compared these values to the experimental value, which comes to be around 970.00 megapascal micrometer to the power half. This is the final overlapping region that we are trying to highlight here. This is the build part that we have got from microstructure animation or the microstructure simulations, and this is the part that we have got from the the first one is from macro scale and the second one is from microstructure. And to make a conclusion here that the overlapping is not enough, we even have to uh, we even have to reduce the hatch spacing further to merge the two melt pools or solidified parts. Hence, to if we want to draw some conclusions from the case study that we have done, we can predict surface roughness using AM Pravah. We can know about the melt pool depth, melt pool width, and melt pool height from the previous case study using AM Pravah. We can have an estimate of porosity. We can know cooling rates. We can also have an estimate of complete thermal data, the temperature ranges and temperature gradients, and we can also draw some visual comparisons or visual analysis using Amprava, whether or not the overlapping has happened, whether or not there is a pore formation, lack of fusion defects are there or not, what are the yield stress values, whether there are columnar grains or equest grains in the system, the Marangoni convection is right or not, the keyhole formation is there or not, and what are the grain sizes and how the mechanical properties look like. So this AM Pravah for using LPBF simulations will give you enough data to minimize your experimental uh, design of experiments, and which can cut down your cost and which can significantly reduce the simulation time for you, experimental time for you. So now I will hand over the floor to my colleague Monish Soral, and over to you, Monish.
Thank you, ma'am. Let me share my screen.
Yeah.
Is it visible?
Yes.
So, hello everyone. I'm Mohnish Soral, Research and Development Engineer at Paanduv Applications. We have heard a lot of demand regarding a CFD module for simulating wire laser additive manufacturing from people across AM industry and academia. The wait is finally over. The AM Pravah 2.0 is coming up with a WLAM module, and today I'm going to present a few case studies carried out in AM Pravah to determine the impact of variation in process parameters and its effect on the deposited dimensions of the deposited bead. Let us begin with some physics, multi-physics aspects of the DED processes. DED processes usually involves a heating source for melting the feedstock, and the feedstock is melted and it is deposited layer by layer over the substrate. So in this process, we have the laser absorption and reflection. We have the multi-phase physics of melting, solidification, and remelting. We also have various modes of heat transfer, such as radiation heat transfer, conduction heat transfer from the deposited part, build part, and to the substrate. We also have convection heat transfer, both from melt pool and the new build part. So all in all, direct energy deposition processes is a complex intermingling mingling between various disciplines of the physics. So direct energy deposition can be classified based upon the type of heat source used. We can either use beam, which can further be classified as electron beam and laser beam. And if we are using an electric arc as an heat source, then it can be classified as TIG, plasma, gas metal arc welding. So we have in this image, a typical setup for WLAM is shown. we have a wire feeder through which the feedstock is delivered, and then we have a laser for melting as a heat source for melting the wire, and we have a substrate on which the feedstock is deposited. We also have a shielding gas for protecting the melt pool from contamination and oxidation. There are 6 key process parameters, including laser power, laser spot diameter, wire feed rate, deposition speed, wire feed angle, and shielding gas flow rate, that affects the shape and size of the deposited bead and hence the overall mechanical properties of the build part. Now, where do we use these DED processes? So, as you can see in the on the image in the left hand side, that NASA, in collaboration with Osborne University, has manufactured a 2 tons nozzle with direct energy deposition process. And on the right hand side, there is a comparison between the LPBF process and DED process. So it is clearly visible from the plot that DED processes are much more capable of manufacturing wider range of component sizes. Then here we can see that it took around 90 days to manufacture a component with LPBF. On the other hand, it took less than 14 days to manufacture a component with the same component with the direct energy deposition process. So basically, the direct energy deposition processes took lesser time for manufacturing. Direct energy deposition processes are also used for component repair because the heat inputs are lower and controlled. Due to that, the distortions and stresses are minimal inside that repair in the component. Also, the cooling rates are quite significant in direct energy deposition processes, and they are cost effective, which makes them a good choice for repairing the components. Now you might be thinking, why do we need CFD for simulating W-LAM process? So let me answer this. Computational fluid dynamics can significantly aid the additive manufacturing process by capturing the multiphysics aspects based on process parameters and provide a clear insight into how, when, and where the defects may occur, and which can then be used to optimize the process parameters to improve the overall build part. In the image on the left hand side, you can see that we have simulated a complex set scan pattern with AM Pravah, and AM Pravah is capable of capturing defects like groove formation and bulges. On the right hand side, we have simulated a single bead deposition, and we are able to capture with AM Pravah the hump formation in the deposited bead. Let's start with the case study. The aim of this case study is to identify the impact of process parameters, like how the laser power and deposition speed are affecting the dimensions of the deposited bead size. The process parameters we took for this as feed angle 25 degree, the spot diameter is around 3.8 mm, the wire diameter is around 1.2 mm, and the wire speed is around 1 meters per minute. The material properties for the simulation are chosen as Ti 6Al4V. For the case of variation in deposition speed, the laser power is capped as 1200 watts, and 3 different deposition speeds of 0.48 meters per minute, 1.2 meters per minute, and 1.44 meters per minute are chosen. On the other hand, for the variation in laser power, the deposition speed is capped as 0.96 meters per minute, and the laser power, we have taken 3 different laser powers: 800 watts, 1200 watts, and 1600 watts. So in case of 0.48 meters per minute of deposition speed, Big droplet transfer is observed, as you can see in the video on the left hand side. While in the case of a deposition speed of 1.44 meters per minute, there are small droplet transfer is observed, as you can see in the video on the right hand side. Here are some results from the AM Pravah. For the case of 0.48 meters per minute of deposition rate, the bead height is around 0.99 mm and the width is around 3.47 mm. For the case of 1.20 meters per minute of deposition speed, the bead height is 0.57 mm and the bead width is around 2.72 mm. And for the final case of 1.44 meters per minute, the bead height is around 0.55 mm and the bead width is around 2.55 mm. Here is a comparison of the data predicted by the AM Pravah with the literature. So for the case of 0.48 meters per minute, the predicted width is around 3.47 mm and the predicted height is 0.99 mm. On the other hand, in the literature, it is provided as the width is around 3.3 mm and the height is provided as 1.1 mm. For the case of 1.2 meters per minute of deposition speed, the predicted width is 2.72 mm and the predicted height is around 0.57 mm. And from the literature, it is around 2.5 mm and 0.6 mm of width height. And for the last case of 1.44 meters per minute of deposition speed, the predicted width is around 2.55 mm and the predicted height is around 0.55 mm, 2.55 and 0.55 mm. From the literature, it is given that the width is around 2.3 mm and the height is around 0.6 mm. The average error percentage for the predicted width is 8.25% and the average error percentage for the predicted height is 7.76%. So here are some temporal variation of temperature at the same point at different deposition speeds. As we can observe from the first curve of 1.44 meters per minute of deposition speed, the variation in temperature is much more steeper. On the other hand, for the case of 1.20 meters per minute of deposition speed, the variation in the temperature is less steeper for the same point. On the other hand, for the case of 0.48 meters per minute, the change in temperature at the same point is much more gradual due to the slower speed of the laser. Then for the case of variation in the laser power, we have observed an intermittent liquid transfer for a laser power of 800 watts, as you can see in the video on the left hand side. And on the other hand, when the laser power is 1600 watts, there is a liquid bridge transfer was observed, as you can see in the video on the right hand side. So these are the results of the predicted width and height of the deposited bead from AM Pravah. For the case of 800 watts, it is around 0.76 mm, and for the width is around 1.86 mm. For a laser power of 1200 watts, the bead height is around 0.65 mm and the bead width is around 2.95 mm. For the case of 1600 watts of laser power, the predicted height is 0.58 mm and the width is around 3.35 mm. Here is a comparison for the variation in laser power from the literature. So the laser power for the laser power of 800 watts. The predicted width by AM Pravah is around 1.86 mm, and the predicted height is around 0.76 mm. From the literature, the width is 1.7 mm and the height is 0.8 mm. For the case of 1200 watts of laser power, the predicted width is around 2.95 mm and the predicted height is around 0.65 mm. And from the literature, the width is 2.7 mm and the height is zero point 0.7 mm. For the last case of 1600 watts of laser power, the predicted width is around 3.35 mm and the predicted height is around 0.58 mm. From the literature, it is around 3.1 mm for the width and zero point 0.6 mm for the height. The average error percentage in the predicted width is 8.72% and the average percentage error in the predicted height is around 5.15%. So AM Prava provides a quite closer results to the experimental, and the accuracy can be improved by increasing the mesh size. These are the temperature versus time curve for the variation in the laser power and at the same point, and we can see that for the case of 800 watts of laser power, the peak temperature is around 2600 Kelvin, while for a 1200 watts of laser power it is around 2800 Kelvins, and for the case of laser power of 1600 watts it is more than 3000 Kelvins. AIMPROVA is also capable of simulating complex and multi-layer patterns. As you can see in this video, we have simulated a complex Z pattern, which is a multi-layer pattern. The properties for this pattern, the material properties we have used are of Ti6Al4V. The laser power is around 1000 watts, and the feed angle for this case is 45 degrees, and the feed rate is around 0.017 meters per second. So to conclude, for the laser power variation, the maximum bead width is around 3.35 mm and the maximum bead height is around 0.76 mm. The maximum cooling rate is around 6.9 into 10 to the power 3 kelvins per second, and the bead temperature range is around 900 to 1800 kelvins. While on the other hand, for the variation in deposition speed, the maximum bead width is around 3.47 mm and the maximum bead height is around 0.99 mm. The maximum cooling rate for the case of variation in deposition speed is 1.5 into 10 to the power 4 kelvins per second, and the bead temperature range is around 1100 to 1900 kelvins. AM Prava is also capable of providing data regarding the depth of the bead. AM Prava is capable of predicting defects such as grooves, bulges, and humps. The process parameter optimization can be done depending upon the results obtained from the simulations. AM Prava is also capable of multi-track depositions for WLM processes. And we can also simulate complex scan pattern with the help of AM Prava. I will get back to Dr. Imjim for concluding the today's session.
Thank you, Monish. I'll just reshare my screen. So there are some new updates that we are happy to share with all of you, that we are working quite rigorously on the metal mixing and welding processes. And you can see through this animation that there is a thin plate of aluminum at the top of the substrate, which is solid steel, and how prominently the mixing of two when the laser hits the thin plate, the mixing of two metals is happening, and this will eventually translate to including this module in our software, and we are working quite rigorously on that. And we are just a click away from all of you. So if you have any question, any doubt, and you want to connect with us, you can call us, you can write us at support@paanduv.com. You can explore our work and visit our website on www.pandavapplications.com. We are available on all the social media platforms: Instagram, LinkedIn, YouTube, Twitter, Facebook, etc. And you can get all the updates from those social media platforms as well. And you can scan this QR code to reach out to our AM Pravah demo form. You can also get the demo requests and demo PPTs for yourself to explore what we are doing and know our recent updates. Before concluding the webinar, I will just read out some of the comments and some of the questions that we have on YouTube. The first one is, how could someone get a demo of AM Prabha? So you can reach out to us to get the AM Pravah demo, or we have also uploaded one of the demo videos on the YouTube. You can just write to us at support@paanduv.com, or just DM us or reach out to any of the uh, social media platforms. We will connect with you. We will schedule a meeting, and uh, we will give you whatever you require in form of demo. Second is that what kind of defects can AM Prava visualize in a build part? So these defects can be anything starting from the lack of fusion defects, the balling defects, the porosity defects. This may occur because of the air entrapment, or it can happen because of the vapor entrapment into the system, which can compromise with your density, and which can act as the concentrators for defects to happen, failure to happen. And these defects can also be related to any any uh, any visual defects, such as if there are keyhole formation, then and there are some bulges in the structure, you can visualize all of those defects using AM Prava. uh, the next question is, are you guys also working on WAM? Yes, we are working on wire arc additive manufacturing, but we will connect and we will give a webinar once we have got something substantial on that. But we are rigorously working to get the wire arc additive manufacturing. When can we have the DED integration in AM Prabha? Very soon. We are ready with the integration. We will launch the next version of AM Prabha, that is 2.0, in the month of November or early December. And you just stay connected with us for the recent updates. What was the computational time for Z pattern using laser DED? And yeah, it is answered already. 8 hours on 4 processors. All the details related to what are the computation requirement for this software to run, these are all can be provided, but the minimum number of processors can be 4, or it can be little bit higher as well, to run for the preliminary simulations of AM Prabha. And we have made it quite robust, we have made it quite faster, and you can explore our previous webinar through YouTube as well. So now I think, if you have any question, just post us, connect to us, and we'll be just a click away from you. Thank you so much for today, and uh, have a nice day, everyone.
Thank you, everyone.